Every time you see that little padlock in your browser, there's a quiet but remarkably sophisticated protocol doing the heavy lifting behind the scenes. Welcome to Lesson 47, where we're going to pull back the curtain on TLS and SSL, the technology that actually secures the application layer. Over the next few slides, we'll walk through the handshake, certificates, and the public key infrastructure that makes trust on the internet possible. Here's the path we'll take together. First, we'll nail down exactly what TLS protects, the 3 core guarantees it gives every secure connection. Then, we'll trace the handshake itself, step by step, to see how a session actually comes to life. From there, we'll dig into X0509 certificates and the PKI trust chain that makes the whole system believable. And finally, we'll compare cipher suites and see what changed between TLS 1.2 and the much leaner 1.3. So let's start with what TLS actually gives you. There are 3 core guarantees plus 1 valuable bonus. Confidentiality means eavesdroppers only see ciphertext, your URL paths, form fields, and cookies stay hidden, thanks to symmetric ciphers like AES-GCM. Integrity ensures any tampering is detected and rejected, so a man in the middle can't quietly swap a download. Authentication, backed by X509 certificates and trusted CAs, proves you're really talking to bank.com and not an imposter. And the bonus, forward secrecy, delivered by Ephemeral Key Exchange, means even if a private key leaks tomorrow, today's traffic stays safe. Before we dive into the handshake, a quick look at where TLS came from and where it lives. It started life as SSL back in 1995, but both SSL versions are long broken. Poodle killed SSL 3.0 in 2014. TLS 1.0 and 1.1 are deprecated and gone from browsers since 2020. Today, 1.2 is still widely acceptable, but 1.3 from 2018 is the modern preference, simpler, faster, and more secure. And structurally, TLS sits right between your application and TCP, unlike IPsec, which operates down at layer 3 across the whole network. So let's see how 1.3 actually delivers all of this in a single round trip. The client opens with a client hello, carrying its supported ciphers and, crucially, its Diffie-Hellman key share up front. The server picks a cipher, sends its own DH share plus the certificate chain already encrypted, and proves it owns the private key with finished. The client confirms, and from there, application data flows encrypted both ways. One round trip to security where TLS 1.2 need 2, and with session resumption, 1.3 can even go to 0. Now, that certificate the server sent, what's actually in it? At its core, an XFOM 509 cert binds a public key to an identity, and a trusted authority signs that binding. The subject says who it's for. The issuer says which CA vouched for it. Validity dates bound its lifetime, and the SON field lists every host name it covers. That's what your browser actually checks today, not the old common name. The CA's signature over all of this is what makes it trustworthy, and you'll meet these certs in 3 formats: PEM for text, DAR for binary, and PKCES Russian 12 when you need the key bundled with it. But who signs that CA's signature? That's where PKI, the public key infrastructure, comes in, and it's structured as a chain. At the top sit around 150 root CAs like DigiCert and Let's Encrypt, self-signed and pre-installed in your browser or operating system. Roots almost never sign your cert directly. They sign intermediate CAs, and those intermediates sign the leaf cert your server actually presents. When validating, your browser walks up that chain, verifying each signature with the parent's public key until it hits a root it already trusts. If the chain holds, the host name matches, the dates are valid, and it's not revoked, you get the green padlock. With trust established, the client and server still need to agree on which crypto algorithms to actually use, and that's the cipher suite. Take TLS ACDEAA Arza with ES 250 GCM. Yes, 384. ECDI handles key exchange with the forward secrecy. RDT authenticates the server via its certificate. AES 256 in GCM mode encrypts the bulk traffic while also guaranteeing integrity in one shot. And SHA 384 backs the key derivation. 5 moving parts, 1 negotiated menu. TLS 1.3 cleans this up dramatically. Only 5 suites remain because key exchange and authentication are now negotiated separately from the cipher itself. So, how does this all come together operationally? It's a 6-step life cycle. You generate a private key and CSR, submit it to a CA. These days, usually automated through ACME with something like certbot. Then the CA validates that you actually own the domain, typically by dropping a token at a well-known URL or a DNS record. Once verified, the CA issues your full chain, you deploy it to your web server or load balancer, and then, critically, you monitor and renew before expiry. With Let's Encrypt certs only valid for 90 days, that last step isn't optional. It's a cron job, and forgetting it is how production outages happen. And when that life cycle breaks down, you'll meet these errors in the wild. Cert authority. Invalid means the browser doesn't trust the signer, usually a self-signed cert. Swap it for a public CA or distribute your internal root. Cert date. Invalid is either an expired cert or a skewed clock, so check NTP on both ends. Common name mismatches mean you forgot a SON entry. Add every host name you serve. Version or cipher mismatches point to an ancient server stuck on TLS 1.0. Enable 1.2 or higher with AEAD suites. And mixed content warnings happen when an HTTPS page pulls in plain HTTP assets. Every sub-resource needs to be HTTPS too. To debug those errors, OpenSSL is your best friend. The S-client command opens a live TLS connection so you can see the server's certificate chain, the negotiated protocol, and the cipher in use. And you can force a specific version or suite to test compatibility. The X509 subcommand inspects cert files directly, pulling out expiry dates or every field for a full decode. And when you want a second opinion, SSL Labs gives you a graded report card covering protocols, ciphers, and known vulnerabilities in one shot. So let's pull it all together. TLS is the universal security layer for applications. It sits above TCP, below your protocol, and delivers confidentiality, integrity, authentication, and perfect forward secrecy. Stick to 1.3 where you can, 1.2 at minimum, and disable everything older. Remember, the handshake is now a single round trip. Trust flows through the X509 chain from root to leaf. And the cipher suite bundles your key exchange, authentication, encryption, and MAC into one negotiated choice. Master the certs, and you've mastered the modern web. And here's your reference card for everything we just covered. Keep this close. It's the quick lookup for TLS versions, the anatomy of an X509 certificate, the structure of PKI, and how cipher suites are built in 1.2 versus the streamlined AEAD only, set in 1.3. When you're configuring a server or debugging a handshake in the wild, these are the terms and patterns you'll reach for again and again. And that wraps up our deep dive into TLS and the application layer. Next up in Lesson 48, we shift perspective entirely from securing connections to rethinking trust itself with zero trust networking. We'll explore Google's Beyond Corp model and how microsegmentation enforces the principle of never trust, always verify. I'll see you in the next lesson.